Hello, people. My name is Arvind, and today I'm going to explain a beautiful concept that it's actually more of a shock because people think that Newton's laws work everywhere, right? The most important laws of motion, as far as classical physics is concerned, actually they do not work everywhere. You people thought that they're universal, but now you know that they aren't. Let's see why. So, before understanding the crux of this matter, I want to clear this misconception in most of your minds, where you people think that Newton's first law is actually derived from Newton's second law, right? You have the equation of Newton's second law where mass is constant, F is equal to ma, and you say that if acceleration is zero, then your net force on the mass is zero, and hence you say that the block is going with constant velocity or it is at rest. This concept is wrong because actually the Newton's second law is derived from the Newton's first law. We make a very important assumption in Newton's first law, right? Newton's first law states that a body can resist its state of rest or uniform motion unless and until there is external unbalanced force applied on the object, right? But we make a very important assumption that this only works in inertial frames of reference. Now you will ask me what are they? Of course, right? That is the question, most basic question you will ask. So before understanding why Newton's laws don't work, I will explain you the two important frames in physics or in classical physics we deal with, right? So first frame of reference is called inertial frame of reference. But before understanding this, but before understanding this concept, I want to explain what a frame of reference is. A frame of reference is a very important thing in physics because that is the one that will describe the motion of any particle. Just take a simple example. Okay, you are sitting in a car. I am looking at you, and I am actually just standing and I'm looking at you. Now, with respect to me, you are moving. If I weren't there, you wouldn't know if you were moving or not, right? So, you always take the information of motion from the frame of reference you are taking, right? Now, let's talk about inertial frame of reference. First of all, let us understand what inertia is. Inertia basically means the tendency of any body to resist its state of rest or uniform motion, right? This is what inertia is, right? You must all know this. So that means the acceleration of the block is always going to be zero, right? Right? The acceleration of the observer is going to be zero, not the block. My bad. Now let's take a simple case. Okay, and before taking the simple case, I want to tell you if acceleration is not zero, that frame is that of the frame of reference is not zero. That frame is called non-inertial frame of reference. Fine, this is it. Inertial frame of reference, the acceleration of the frame of reference is zero, or the coordinates of the frame of reference are going with constant velocity or they're at rest. If it's a non-inertial frame of reference, the coordinates of the observer or the frame of reference are going with some acceleration. Right? Very simple. Now let's take a case where there's an elevator and there's a block of mass m inside, just standing on the surface. And this elevator is going up with an acceleration a, right? It can either go up or go down. That is the case of an elevator, like in the most general cases. So now, and I am looking at this situation by standing outside, right? I'm just standing. I'm not moving with a constant velocity or I'm not moving with any acceleration. I'm just standing. That means I'm an inertial observer because that is what the concept of inertial frame of reference says. Okay, cool. Now I am going to I'm going to write an equation for this mass m. So first of all, to write the equation, I will draw a free body diagram. Now, what is a free body diagram? A free body diagram is basically the representation of all the forces that are acting on the body. Never ever make this mistake. of showing all the forces the body is applying on another body. That is a completely wrong concept. You must always, always, and always represent the forces that another body is applying on that particular body whose free body diagram you are drawing. So here I'm drawing the free body diagram of mass M. So generally to draw free body diagrams, we take the whole mass as a point mass because then our diagrams don't become very lengthy and it's very easy to draw. So basically we are assuming that the whole mass is concentrated at a point mass. Okay. Now let's draw the forces. The earth will be attracting this block with the force mg, right? Gurutwakarshan, gravity, right? And what is making this block sit on the surface? The surface is of course applying a force on the block, right? So this force is called the normal force, right? It's called the normal force, or sometimes it's called the normal reaction denoted by N. So basically, normal force has a very important property in physics, right? So normal force is only applied when two surfaces are in contact, such that the normal force is always perpendicular to the plane of paper, right? Even in light, you would have learned the laws of reflection, right? The incident ray, reflected ray, and normal are on the same plane. That normal is what? It's always perpendicular to the plane, right? So normal anywhere is always perpendicular. You've even learned this theorem in maths where the radius is always normal to the circumference of the circle. So normal means perpendicular. And here the surface is applying a force on the block which is perpendicular to the surface, and this force is called the normal force, right? And this whole body is accelerating upwards with an acceleration a. This is your free body diagram. Now, from Newton's second law, we know that net force equals to ma, and I will say that n minus mg, sorry, n minus mg equals to ma. Right? This is my equation. Nice. But now let me make myself a non-inertial observer, right? Non-inertial observer means I must have some acceleration. My coordinates should have some acceleration. So let me put myself inside the lift. Now I'm observing the case. Okay. Now when I'm putting myself in the lift, you must understand that this is a very important situation. Look, when I'm putting myself inside the lift, I am not observing any acceleration of the block end because, look, I am inside the lift. I don't have any reference point to say that the mass is accelerating because I'm inside with the block. I am moving with the same velocity with which the block is moving. I'm moving with the same acceleration the with which the block is moving. So there is no relative acceleration there, and that is why I am not able to observe any acceleration in the block. Right. So in that case, I will say that my acceleration is equal to zero, and from Newton's first law, if acceleration is zero, your net force is zero, right? So I will say n minus mg is equal to zero, or n is equal to mg. Now, you tell me, guys, if I am observing from outside and if I'm observing from inside, how can there be two different cases? Think about it. I am observing something from outside and I'm observing something from inside. I cannot say that there are two different cases. That is not a good argument at all, right? And this is why Newton's laws never work in frames where the frame is accelerating. See, here you got an equation n minus mg equals ma, which is absolutely perfect. But here you're getting n is equal to mg. This is wrong. And that is why Newton's laws don't work everywhere. Now you will ask me how to repair them. This is the beautiful concept, which is called pseudo force, right? I'm going to explain it here, right? Pseudo force. You would have learned in biology pseudopodia, right? Or you would have heard of this term called pseudo feminism, where pseudo is a very common word, right? Pseudo basically means false, right? Pseudopodia, false feet. Simple. Pseudo force. So, to make sure Newton's laws are working in non inertial frames, we are using a pseudo force. But pseudo force is not a force that is being applied in real life, right? Remember that concept. It is not something that is actually being applied just for making physics correct. We are using this concept called pseudo force, right? Let's take the same situation here. I'm going to just transpose this here. So, this is our block M and we are observing from inside. Remember only to apply pseudo force when the frame of reference is inertial or the frame of reference is accelerating. right? The coordinates of the frame of reference is accelerating. Coordinates as in the coordinate system, right? These are the coordinates x, y, and z axis, right? Cool. Now, look, pseudo force is basically when you are in a non-inertial frame of reference and you want to make Newton's laws work. So let's draw the free body diagram of this mg, downwards, simple stuff, and normal force. Now, you must also apply a pseudo force such that your Newton's laws work. So what you do is this pseudo force. See, remember you had this equation where initially n minus mg is equal to ma, right? You want to get this even when you are in a non-inertial frame of reference. So what you do is this ma in the right hand side, right? Initially, this is an upward direction, right? The whole net force is in upward direction when you are an inertial observer, right? But when you've become a non-inertial observer, you have to apply this pseudo force, and this pseudo force is always applied in the direction opposite to the direction of motion, right? And this pseudo force formula is basically your F, right? I'm denoting with F is equal to minus ma. This minus is basically direction. So this ma is always applied in the opposite direction. So you will apply ma in this direction, right? This is your pseudo force. Now, again, you just see the block in rest. You just see the block as it is at rest because you don't see any movement. So n is equal to mg plus ma, and again you get the equation n minus mg is equal to ma. So pseudo force is basically a concept that is theoretical, like white holes. They don't really exist. So pseudo force doesn't really exist, but just for making physics work, we use this concept, right? So pseudo force is equal to minus ma, where you're applying that ma force in the opposite direction of acceleration, such that you are a non-inertial observer, right? So this is the concept of pseudo force. Okay, and this is why Newton's laws don't work everywhere. Cool. Thank you.